This is not... This is a way of looking at the radiation. And we have that up on the screen now. Maybe turn on the lights, you can see it better. We turn down the lights a bit. Let's see what we can see. This is what's called a cloud chamber. A cloud chamber is a bit of gas. It has air and alcohol in it. And the purpose of the alcohol, it has dry ice underneath it. And what we do is you cool it until it's about to turn into a cloud. And you can see there are little clouds that form now and then. These are just the conditions where there's so much alcohol in the air and it's cold, and it tends to form a cloud. And Wilson discovered that when you do that, it tends to form clouds around in little streaks. We now know that these streaks, there's one over there. See that go by? These streaks are actually, ooh, look at that one. That went like that. And then because of a little bit of breeze, it broke up. But what you're doing is forming clouds along these paths. We now know that these paths are paths of radiation. So a particle, radiation, some kinds of radiation turn out to be electrons. Some of it turns out to be nuclei. Pieces of nuclei are, when they're moving, shot out from this nucleus at very high speed. Then they make a cloud form along it. There was a piece shooting out like that. This one is probably coming up, so it looks kind of funny in shape, going that way. And there's a little one there. And you see these things every now and then, little one there. And you see them forming. So what is happening, we now understand, is that when you have the radioactivity, in some cases the nucleus breaks up, pieces go flying out. The piece could be a fragment of a nucleus which has protons in it. One of the most common ones turns out to be called an alpha particle. An alpha particle has 2 protons. Another piece that comes out is an electron. The beta rays turned out to have been electrons. Alpha particles have 2 protons. Beta rays so the alpha particles are pieces of nuclei consisting of two protons. They also have 2 things in them called neutrons. Beta rays are these electrons coming out. What happens when they come out? Let's talk about the dangers of radioactivity and what it does and why some of it, why I wear this but not the wristwatch, not this other wristwatch. So I'll get the lights back on. And let's talk about what happens when one of these fragments goes flying out. Yes? Yes. The question is, does that mean that alpha particles are helium nuclei? It turns out alpha particles are identical to the nucleus inside the helium.
I want to do some more things in mine.
That turns out to be very interesting. In fact, let me digress on that for a moment while I remember. Because when these nuclei break up, one of the pieces, one of the small pieces that comes out is typically a fragment of a nucleus consisting of 2 protons and 2 neutrons. A neutron is a third particle that's just like a proton except it has no charge. It has no charge, but it does have gluons, and so it helps hold the nucleus together by adding more gluons without having the repulsion of the charge. So a helium nucleus has 2 protons, as I said, but it has 2 of these other things in it called neutrons that just help hold it together. And if they hold it together so well with 2 protons and 2 neutrons that when pieces come flying off a big nucleus, very frequently one of the pieces is an alpha particle, namely a helium nucleus, namely 2 protons and 2 neutrons stuck together. So imagine this explosion, and the pieces come off, and one of these pieces is a brick, a small particle consisting of 2 protons and 2 neutrons. This goes flying off at high speed. It has charge. It has electric charge. Because it has electric charge, whenever it passes by anything else, like an atom, that atom, the electrons of that atom are attracted to that charge. They may be pulled away from their own nucleus. You may turn one of these atoms into an ion. Here's what I want you to visualize. This nucleus blows up. One of the pieces that comes flying out is a charged alpha particle, 2 protons and 2 neutrons. It goes flying through matter. As it does that, it passes by a nice, neutral, happy atom. But the electron in that atom sees this positive charge coming near. It's attracted to its nucleus, but it feels this too. It may get ripped off. And that's typically the damage done by radiation, is that it knocks electrons off atoms. That's the key mechanism. When you knock an electron off an atom, you don't have that atom anymore. You have a charged atom. If you knock one electron off carbon, carbon has 6 protons and 6 electrons. There it is. Atomic number 6. 6 protons, 6 electrons, plus some more neutrons. Typically 6 more neutrons. You knock an electron off, and now you have a charged atom. Not surprisingly, an atom that has charge behaves quite differently from an atom that's not charged. It may be very reactive. Those of you who study chemistry know that ions are very chemically reactive. Suppose it's part of a water molecule, and you knock an electron off. The molecule itself may go flying apart. Suppose it's part of your DNA, the oxyribonucleic acid, the molecule that encodes all of your genetic information and how to run the cell. If you knock an electron off one of those atoms, you can basically break the DNA, put in what's called a mutation. The cell may not function anymore. DNA will come along, and it has these marvelous mechanisms that we've only been discovering in recent years. It has chemicals that actually move along the DNA and look for mistakes, things that were damaged by radioactivity. And it will sometimes fix them up and then move on. But if you get enough of these damaging alpha particles coming by, and they break enough places in the DNA, the cell can just die. Or even worse, if the disruption is just done in just the wrong way, the cell gets out of control of itself. It starts replicating. The mechanisms that keep it from replicating now are turned off. It starts dividing like it did when you were a little baby. And that's called cancer. So the damage done to the cells is by these particles flying by, disrupting the atoms, knocking off an electron, changing the chemistry. At this point, a zillion different things can happen. The nicest one that can happen is it just kills the cell. You get a lot of that happening. Suppose I'm exposed to a lot of radioactivity, and a lot of my cells get killed. Well, I don't need all my cells, but if enough of them get killed, and there's enough damage, I'll die. That's called radiation poisoning. With less radioactivity, not enough to kill my cells and kill me, but it may do some genetic damage. And the one that is probably the most dangerous is to form mutations that will trigger cancer. And so radioactivity yields radiation. The radiation goes through my body. It knocks off electrons. The electrons change the chemistry of the atoms. They disrupt the DNA. The DNA now loses its ability to control the replication. Replication goes wild. We have cancer. So this is how radiation does damage. How much radiation does it take to do these things? Well, how do you measure? These are some of the most important numbers I'm going to ask you to remember. I'll put them on the board. Whenever there's a number I want you to remember. But these have to do with radiation damage, and you'll find this enormously useful when thinking about nuclear reactors, nuclear bombs, radiological weapons, whatever. So to quantify this, people have asked, well, how much damage is done by a certain amount of radioactivity in my body? And before they understood the mechanisms, they came up with a unit called the Roentgen, named after the discovery of X-rays. And what they did is they say this energy, these particles, are going through, and they're knocking electrons off, and eventually these electrons go off to get the chemical reaction. Most of the energy eventually turns into heat. So all they did was to determine how much a piece of water heats up when you put radioactivity next to it. And that way you can measure the danger of radioactivity. Now, it's not the heat that's doing the damage. The heat is a byproduct. But the assumption was, well, it probably is the more radiation, the more heat, and so on, and so let's consider that. That was called the Roentgen. They eventually changed that to the REM. I guess maybe the Roentgen was, they had different ways of doing it. The amount of charge released, the amount of heat released. One of them was the REM, one was the Roentgen, and then they figured out really how much damage it does, and they called that the Roentgen equivalent. You don't have to know all this stuff. Just what I want you to know is that when we measure damage the unit that they finally came up with was called the Roentgen equivalent for man, which is the rem. And you don't even have to know what rem stands for. It stands for Roentgen equivalent for man. And you don't have to know that because that's unimportant. The thing you have to know is that we use the rem to measure the radioactivity, the damage done to a cell.